Hey folks, y'all doing okay? Listen, when is the next exam after the 8 o'clock? Is it a noon exam? 10:30? Is that right? Okay. All right. Y'all have a 10:30 exam? Would you? I was gonna give y'all an extra half hour because usually we have more than an hour, so I was gonna give y'all an extra half hour. Would you mind coming in at 7:30 instead of 8? Would you like to come in at 7:30 instead of 8? I don't think you'll need it. Like I think 2 hours is enough. There are 28 multiple choice and 7 free response. It's roughly twice the length. It's a little less than twice the length of a regular exam. So I know it seems long, but it's almost twice the length. You aren't going to decide, are you? You just want me to decide? Yeah, I understand. That just puts me there for 3 hours instead of 2.5. No, it's going to be in Palcha Auditorium. Y'all are comfortable in there? Okay. Bring a jacket. It might be cold. All right, let me think about it. I think 2 hours is plenty of time, but let me think about it. Maybe I'll just get there 15 minutes early, and then I'll let y'all stay 15 minutes late or whatever. But give everybody the full 2.5 hours. I'll send y'all an email tonight, okay? Um, all right, so like I said, it's 28 multiple choice questions and I think 7 free response. I'm pretty sure there are seven, maybe six. No, there are 7 free response. And 110 points are in the free response. Y'all tend to do better in the free response. So I tried to load a lot of the points in that. But anyway, and then the remaining 40 points are in the multiple choice. Told y'all this, but let me just sort of recap. So, like for example, the very first question that you have is a an estimation problem, but it's not this estimation problem. It's something else, right? So something that I ask you to find the area or the volume of, and it's something that you know, something that you've seen before. So with those estimation problems, for example, just know what a centimeter is, know what a meter is. Don't worry about mass estimations. You're just going to do either volume, area, or length. Know what a centimeter is, width of your pinky. Know what a meter is, a few feet long, and then from those estimations, be able to find the area or the volume. So you'll have something like that where I change the same problem, but I just sort of change the context of the problem or what it's about. You'll have dimensional analysis, for example, where I give you an equation and ask you, is it dimensionally correct or not? Um, Things like that, so I'll change it in that way. You'll also have a standard of measurement question, but it may or may not be the meter. It might be something else, so you need to know the standards of measurement. I think that y'all know most of those. I think that y'all are pretty good. You have a trig problem, you have these problems. We'll sort of spend more time on these. Just want to give you a flavor of sort of how I'll change the questions and what to expect. Like, for example, you'll have one of these where you have to interpret a position or velocity versus time graph, but it won't be this graph. It'll be a similar but different graph. Um, on the free response, you'll have, um, you could have something like this, a graphing problem, but with a different graph. Okay, but I maybe even some slightly different questions. Uh, Although here, that's about what I could ask on that. You could have a a problem like this, a simple kinematic. This one's fairly simple kinematics problem, though you had more complicated ones. But I'll just change the numbers, maybe. Maybe I'll just change the numbers, or maybe slightly change what I'm looking for. Okay. But if you can work through these problems, you should be okay. You know, you're going to see some of them, and you're going to say, "Gosh, that's just like the test, except just different numbers," and that's good. Hopefully, you'll be good to go on that. And then others you'll see and say, "Well, gosh, that's really a lot like the test problem, and I work it the same way." And then others will be a little bit more different. Uh, and we'll talk about that as we go through the test. Okay, you will see some integrals and derivatives. Make sure you can do those, and also make sure you know what they mean, right? That the velocity is the derivative of the position, the acceleration is the derivative of the velocity. To find the distance traveled, you do the integral, that sort of thing. And then also, we had some with work and energy that were related as well. Um, So that's sort of what you should expect, and hopefully you've been working through those exams, so you're all okay with those, more or less. Well, be careful though, because like I said, the questions are slightly different, and so if you've been working through the exams a lot, you might be sort of, you know, this is what I do, this is what I do. So make sure that you read the questions carefully, and if what you do is a little bit different, that you're prepared for that. Okay? All right. Particular questions about exam one, and today we'll go through the 4 exams. Excuse me. We'll go through the 4 exams and look at each one. So particular questions about exam one. I'll go back to the beginning. We'll begin looking at the multiple choice. So holler out if you see something. On this page we had estimation. Yeah, this number 3. And you'll see one like this. In fact, I think it's this question, but I just gave you different equations. So make sure that you can do it. So on these, you want to put in the dimensions for each of the equations. So for example, number 1 is velocity, that's meters per second, but it's squared. Both of them are squared. V naught is also meters per second. They're both squared. The 2 doesn't have units. A is meters per second squared times x is meters. So all of these check out to be meters squared per second squared. So this one's good. Here I have 1/2 mv squared, that's kilograms meters per second, but it's squared, plus xma, that's meters, kilograms, meters per second squared, equals kilograms, meters squared per second. That is not dimensionally correct because, see, both of these are the same, but this one is different because the meters is squared instead of the seconds. And then this third one, so this is not good. The third one is meters per second on this side, meters per second on this side. So this is okay. So it's just 1 and 3. You want to be able to do that. Put in the units for each variable and then tell whether it's dimensionally correct or not. Does it match up on either side? Okay? I think that's question 2 on the test. Don't forget your standards of measurement. For meter, it's the distance that light travels in a particular time. For time, it's based on the cesium atom. For the kilogram, remember it's a cylinder in France. Okay, you will have a trig question, but you know that should be a gimme for y'all. Y'all are good at that. Y'all can work these problems like number 13 and 14. You will have to do that. Remember, on these you're looking at the if you're looking at position versus time, the velocity is the slope. If you're looking at velocity versus time, the acceleration is the slope. So for example, here on number 14, I start with a small negative slope and end with a big negative slope. So I look here, I start with a small negative slope, end with a big negative slope. I'm looking at the numbers on the axis. So like this is -1, this is -4, just to put some numbers in there. And so you're looking at what is the value of the slope doing. You will have something like that. All right, anything here in particular? Okay, how about on the problems for test number 1? If it, okay, so if you have a v versus t graph, the distance traveled is the area of that graph, which remember the area is just the integral. So if I want to find the total distance traveled, I take the integral, or if I have the graph, I just find the area depending on what my time interval. I was going from 1 to 3 seconds here, so I define the area under that graph. Does that answer your question? If you have a velocity versus time graph, v versus t, the slope is the acceleration, the area is the distance traveled, x. Okay. Okay, number 16. Even if you're if you think you're okay, but you want me to work through it, I can do that. So number 17. You do have a couple of kinematics problems. Kinematics comes up not only on this test, but also with projectile motion. So you do have a couple of kinematics problems. 17, 18, you will have to deal with a function. Like on number 18, not necessarily like this problem, but this comes up a couple of times where you have to deal with a velocity or an acceleration function. Well, by the way, I can also take problems and sort of mush them together and maybe take a piece from one problem and mush it up with another problem. I did that once on one of the problems. So like, for example, maybe a kinematics problem, and then I ask you something about the function that describes that motion. You follow what I mean? Yeah. Okay. You all good on number 18? Mm-hmm. Okay. Just like we did with the dimensional analysis, right? So we know if we have meters over here, we have to have meters here and here. So this has to be meters per second squared, and this has to be meters per second cubed. Oh, can you repeat your question? In order so that you get matching units on either side. So let's say that 3 is A. I'm just representing 3 as A, and so it's A t squared. So now we're saying that A has units of meters per second squared, and T has units of seconds squared, and so these cancel out, which give us the same units as X on the left-hand side. Right, just like we did in the multiple choice where you're matching up the dimensional analysis, making sure the equations are dimensionally correct, is a similar thing here. All right. Here, to find the function that describes the velocity, you would take the derivative. Make sure you can do a derivative of a polynomial. It would be 6t minus 6t squared. And then the derivative of that to find the acceleration. Okay on this one? Okay. Number 19. This one was a little more complicated, but whenever you approach one of these kinematics problems, just start by writing everything out. In fact, I read this and I don't really know how to start, but once you start writing out what you know and what you don't know, and then write down your equations, then you'll begin to see a way to solve it. Uh, so like for example here, I have this, it's really a two-part problem. My initial velocity is 56 kilometers per hour. You need to convert that. 1 hour is 3,600 seconds, and 1 kilometer is 1,000 meters. I'll try not to have too many just pointless unit conversions, by the way. 56, 16, thank you. And then my distance x is 24 meters, and t is 2 seconds. And I need to know what is the acceleration. So I need to know what is a here. So this car is slowing down, but we don't know what its final speed is. We just know that it's slowing down. And so I know that x is equal to v naught t plus 1/2 a t squared. And I can solve this for a. All right, because I know x, I know v naught, and I know t, so I can solve that for a. And that's fairly straightforward algebra to solve that for a. And then if I want to know the speed at impact, I just say v is equal to v naught plus at, and then solve that for v, and it'll give me the speed at impact. Okay? And then there's the second part of the problem. After it hits the barrier, it starts to slow down. So now whatever you calculated for the final velocity here will become your initial velocity for the second set of the problem, where it's going from hitting the barrier to stopping in 1 meter. Okay? That was a little more complicated. Are y'all okay with this problem? You want me to work through it? Yeah. What did she do? Just use the v squared, v naught a squared. Oh, okay. Okay. Yeah, we could do that. You want to work through this? Okay. Let's work through it. So here, if we find v, my v naught. Do you know what the a is right here? If I solve for a. No, when you solve it here, what is it? -4. And then over here, when I solve for v, it's going to be v naught, which is I'm sorry, 16 minus 4 times t, which was 2. Right, so it's traveling 8 meters per second when it hits that barrier. And then, starting over here, my v naught is now 8 meters per second. My x is 1 meter. I don't know my acceleration, and I don't know t. But I want to know both of those. I want to know both the acceleration and t. I also know that v final equals 0. So I have two equations, two unknowns. You will have to solve a system of two equations, either on this, on a problem like this or a similar problem. So make sure that you can do that, where you have to substitute one equation into another. We've done that on several tests, so y'all should be okay with that. But I have v equals v naught. Say t. Let me just put in the numbers here. I have 0 equals 8 plus a times t, and then I'll have x, which is 1 equals 8t plus 1/2 at squared. You have to solve this equation and then plug that into the other equation. Y'all did t is 8 over a, is that right? Yeah. So t, yeah, -8 over a, and then you can plug this in here and plug it in here, and so you get 1 equals 8 -8 over a. It's just algebra from here, okay? But algebra often causes y'all to stumble a little bit. So when you're going through this, you just need to be very careful. Take a big deep breath. Make sure that you're writing it out very neatly, and sort of following each step. 1/2 a 8 a squared. Yeah, that does work out nicely because you lose one of your a's. Right. So I get -32 over a. All right, and then you solve that for a. I'll leave that, well, I'll finish it off. 1 equals -96 over a. So a is -96. Is that right? Yeah. Oh, this should be positive right here. Right, yeah. All right. If you write neatly, I'll be able to give you more partial credit. Like if you just make a simple mistake like that, I'll knock off 1 point. But if you made that simple mistake, but I can't really follow what you're doing, y'all know this, I won't be able to give you as much credit. So if you write neatly, you'll get more credit if it's correct. I'll be able to follow your work better. Okay? Can I clear this? So make sure you're good on your kinematics. I mean, this isn't the only kinematics. There are several that have come up in the test. So make sure that you're good on those because it does come up on the final. Exam 1, okay? We can come back to it if you want. Let's look at exam 2. Exam 2 looks like we had vectors, projectile motion. You will see some vector stuff. I don't think there was a free response for vectors, for what that's worth. I'm not sure if there's one on this test anyway. But you'll have, what's that? Okay, yeah. You will have questions, like for example, you have one of these where you have to find the right equations. Make sure you can do that. Um, All right. So we'll have to do a projectile motion problem. Make sure that you're good on the different variations of projectile motion. Could be like one like this number 15, but it could be something similar but different. Make sure especially that you're good on these problems where, you know, you start at one level and you end at the same level, and then also where you have something that comes out like this horizontally and travels out like that, that you can work through those. So I could take a projectile motion problem and say this is a projectile motion problem and change it up in one of these ways. But it'll be one of our basic setups. These are sort of our two basic types of projectile motion. So make sure that you can solve both of those. You can look back in your notes. And also, you know, understand projectile motion and what happens there. Know what happens to the acceleration and the velocity vectors over time. That'll come up in the multiple choice. Don't forget your functions, what describes it, what describes the motion. So for example, you know, the y function is this v naught yt plus 1/2 ayt squared. That is our function that describes the y motion, and the x motion is described just by v naught xt. So remember those functions that describe our projectile motion. You're going to have to do some vectors. Honestly, it comes up with an inclined plane. So number 16, you're not going to see something like that. But you will see the inclined plane problem that we had on this. It'll be different, but it will involve an inclined. Sorry, folks, sorry about that. But you will have to do an inclined plane problem. It will have two bodies. You want to look at this one right quick? It'll be similar to this one, but it'll look. I can't tell you that. Oh, I could, couldn't I? Probably not that complicated, Desiree. All right. No, it wasn't that bad. Well, right, right. I get. Mhm. Well, you know what the downside of getting your tests back and sort of having those solutions is that I have to write new tests every year, so you don't see the same problems year to year. Yeah. Okay, so, but the process is still the same, okay? Uh, so on this one, you have to draw your free body diagrams, and I'm going to give you these axes tomorrow for you to draw your free body diagrams, and you'll get credit for part of that. So on these, we had several forces. I'm going to draw them here. So we have our normal force, Fn1, Fw1, and we also had friction acting, so we have Fk1, and we had, I'll call this Ft, and then we had similarly Ft here, Fn2, Fw2, and then Fk2 here. Right, so in this problem, you wanted to know the acceleration and all the frictional forces and the tension. So the way you would do that is by first drawing the axes. Your axes look like this. And you would draw your free body diagrams on the ones that I provided down here. Um, you need to figure out your normal force first. So you want to find Fn1 and Fn2 because you'll need those in order to find the frictional force, right? Because remember our frictional force is mu times my normal force. So I first have to find my normal force, and your normal force is the y component of the weight. That's Fw1 sine of 60. It'd be really helpful if you can just look at that and say, my normal force is Fw sine 60. It's the y component of this force. Notice this angle is 30 degrees, but I do 90 minus that. Okay, we talked about the trig and sort of how that works out, but the y component is the force times the sine of the angle. That's only for an inclined plane. And then this is going to be Fw2 sine of 60. So that's going to be whatever it is. I'm not going to do the numbers here. And then from there, you go and you find Fk1 and Fk2. So that's going to be mu1 Fn1, mu2 Fn2. Your inclined plane will have friction on it on at least one of the bodies. It could have friction on the second body or not. On this case, it had them on both bodies. That's what made it a little more complicated, this problem. Huh? Oh, when you solve for it? Oh, that's nice. So this is 173 newtons. You sure 173? 1.73. All right. So Fk1 and Fk2. And now we're just looking for the acceleration and the tension. And so you still have two unknowns, and you have to make two equations. But you can make two equations, both of which have the tension and the acceleration, by writing the equations in the x direction. So you would say the sum of the forces in the x direction, let's do it for body 1, is going to be Ft minus Fk1 equals M1A1. Being very careful that I get all my subscripts correct, because it is relevant that you get the right mass, that you put in 1 kilogram there instead of 2 kilograms. And then the second one, you would say sum of the forces in the x direction is negative Fk2 minus Ft. Oh, wait, I forgot my force weight. Sorry. This should be minus Fw1. Shoot, I'm sorry, I have a mistake here. Oh, what are we doing? Oh, sorry, let me redo this. For Fw1, you have Ft plus Fw1 cosine of 60 minus Fk1. That's equal to M1AX. Okay, so I'm looking at my free body diagram and realizing that on this side of the origin, this is minus x. On this side of the origin, it's plus x. That's a good question. You're right, thank you. Okay. Right. And when you draw your, Megan, we'll get to it in a second. When you draw your free body diagram here, I think it'll be a little more apparent. I'm sort of drawing it cockeyed, so it doesn't seem as obvious. Megan? Okay, remember on an inclined plane, whenever we're finding the components of the vectors, we always say 90 minus the angle. All right, and then our x component is cosine, our y component is sine. It's because of the trig. You can draw out the triangles, but just remember that. Let's not worry about that right now. Whenever you have an inclined plane, always take 90 minus the angle. Please do that. It makes my job a lot easier for grading. All right. Because it affects every answer that you get. That's Newton's second law. So remember, Newton's second law is that the sum of the forces equals ma. So that's the MA portion of Newton's second law. Whenever you're doing the sum of the forces, it's equal to the mass times the acceleration. Now, often we've been dealing with static problems, and in that case, the sum of the forces is equal to 0. But in this case, it's a dynamic problem, which you will have a dynamic problem where the acceleration is non-zero. You'll be dealing with an inclined plane, it'll have friction, it'll be moving. All right, it may or may not be moving. You have to figure it out, okay? Depending on the friction that's at work. So this was for mass 1. For mass 2, which force is in the positive direction for this one, huh? The force weight. Right, FW2 cosine 60 is positive, minus FT minus FK2 equals M2AX. All right, we have two unknowns in this. Our FT is unknown, and our acceleration is unknown. You have to solve that system of equations. What's that? Okay. I'm not going to solve it here, but you have to solve the system of equations. Okay? So I don't remember how many times you have to solve this. The systems of equations you have to solve aren't terribly difficult, but you know, if algebra is not your strong suit, which I know for some of you it's not, then it will be a little more difficult. But that takes practice. So with your practice, it'll be easier. You could do this problem. The problem on the exam is a little bit simpler than this. You're welcome. Can I clear this? Yeah. Right. Well, this one's a little more complicated because I have two equations and two unknowns. Right. I know this value. I know all of these values. I know everything except for the things in red. Right, because I know FW is just the mass times G. FK we found up here 1.73. And so you have to solve one equation for the acceleration and plug it into the other equation and then solve that equation for FT. Is that what you said? That is what you said. Okay. I'm sorry, I just didn't hear it exactly. Right. FT and A. Those are your unknowns in this case. It's a good skill to be able to look at, you know, a set of equations and know how to solve it. And so you'll see that come up once or twice on the exam. Okay? Can I move on from this one? It's a good question. You'll see it tomorrow. So if not, if you want to dwell on it, we can. Okay, I'm going to clear this. There are some extra credit things, but not the Gaussian elimination. So just sort of like little extra tidbits that you should be able to do, like you should know how to do, but I sort of consider it extra, but not Gaussian elimination. This is similar. You could see something like this. This is similar. It's 2D forces. So what you do with the uh, the inclined plane is similar, although it's only with the inclined plane that we do the whole 90 minus theta. So if you want to know the x and y components of this object, say of Fy is 12 sine of 30, Fx is 12 cosine of 30. Right? It's only with the inclined plane where we do that thing, the 90 minus theta. All right, that was it for exam 2. Anything else on exam 2? Sure. Exam 2? Projectile motion, Newton's laws. You'll see both of those things on the exam. Want to take this down? All right, let's look at exam 3. Let's see, exam 3 was energy and work. We had momentum. make sure you're good with your multiple choice questions here. Like I said, the multiple choice questions will be similar but a little bit different. So for example here, if the momentum of the object is tripled, like I might give you that and say it's doubled or it's halved or something like that. Make sure that you know how to deal with the relationships. I'm not saying that question's on the test, but or I might give you something like this but change the numbers on it, like number 12 here. You will have to do a collision, a momentum. It's a free response question where you have two bodies that are colliding, and I want to know either their initial or their final velocity. It might be perfectly inelastic or an elastic collision. You will not have, excuse me, it might be perfectly inelastic or inelastic. Perfectly inelastic is where they stick together. Inelastic is where just momentum is conserved. You will not have an elastic collision. Remember, we had a take-home question like that where you had to solve for the energy and the momentum. You won't have that here. Um, the algebra is a little too tedious. Number 16, we have conservation of energy. Something similar probably to this. Um, you should also be up to speed on your springs. So I sort of consider that in the same class as this problem. Remember, with your springs, it works very similarly, except instead of having potential energy as mgh, you have potential energy with a spring is 1/2 kx squared. But still, it works out the same way, where our potential energy is transferred into kinetic energy. Sure, you'll have the equation sheet that's on the website, the same one you've been having. That doesn't have chapters 1 through 4 on it, but honestly, there aren't many equations in chapter 1 through 4. Really, all you got is F equals ma and the kinematics equations on chapters 1 through 4. And in fact, the kinematics equations are on that equation sheet, except they're for rotational motion. So if you forget, just remember theta is x, omega is v, and alpha is a. So really just F equals ma. You can just write that on your thumb, and I would never even see it. F equals ma. Don't do that. Serious. Okay. Okay. I remember here with this one, when you have a function like this, if you want to know the work that the function does, it's the integral of the function with respect to x, and then you evaluate that integral over your distance from 0 to x. Nothing funky with your integrals, polynomials. So for example here, the integral of this, the integral of 4x cubed, I add 1 to the exponent, so it becomes x to the 4th, and I divide by that exponent. So it's x, the 4's cancel out, and it's x to the 4th. And then you evaluate at your limits, 0 to x. Okay? Calculus isn't too terribly difficult. I mean, we don't do funky integrals like y'all do in your Calc 2 class or whatever. You see a dot product. Definitely you're going to see a collision. I'm pretty sure you see dot product. I'm not sure. I don't remember, so don't take that as a definite. Your elastic, inelastic. Remember, elastic is, gosh, what's conserved in an elastic collision? What's that? Right, energy and momentum. Right, yeah. And right, yeah. I always think an elastic is like a really bouncy collision. It's very, very elastic. It's very bouncy, so you don't lose much energy in that. All right, that's exam 3. So elastic conserves energy and momentum, and inelastic only conserves momentum. And an example of this is like gas particles, and an example of this is like everything else, like cars colliding. All right? Exam 4. Is this helpful for y'all? Hopefully you're not starting to study tonight. I know it's been, are y'all starting to study tonight? Yeah, okay. So exam 4 was rotation. Of all the exams No, no, that's not true, actually. I was going to say that I pulled the least from this exam, but that's not really true. I think I pulled pretty equally from all four. So on this, like you could see this, like number 2, maybe change a different time, or maybe instead of looking at angle theta, looking at omega. It's really just sort of how do these variables relate to one another. You have the equation sheet, so you should be able to look at the equation sheet and tell, is this a quadratic or a linear relationship? But like for example here, students often have trouble with this. Theta is 1/2 alpha t squared. You know, if I double my time right here, because that t is squared, I quadruple my theta. And if it was omega, for example, omega is alpha times t. If I double my time, I only double my velocity. You could have something like 5, except maybe a different shape. Right? So remember with this, the moment of inertia is mr squared. Um, and so you're looking for the biggest moment of inertia is where you have the most mass at the biggest radius. The most mass at the biggest radius. That makes your moment of inertia bigger. That's what we did here. What's that? Torques, and then lenses. That's all we had on this test. Yeah, just torques and lenses and mirrors. You will need to know what types of images are formed by what types of lenses. So you have a question that's similar to this, but the object and image are different, you know, different perspective to one another. So know what forms what kind of images. I can summarize it for you if you want. We have a concave mirror. This is like your shaving mirror. You can either have like this. Actually, no. The image is actually. Oh wait, no, 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 no. You're right. I'm sorry. Hold on. So with a concave mirror, your image. This is my object. This is my image. This is my object. This is my image. Remember, for mirrors, the real image is formed on the same side as the object. For lenses, the real image is formed on the opposite side of the object. So for example, this image is a real image. This image is a virtual image. Knowing what types of mirrors and lenses form what types of images will help you in the free response problems too, because you often have to know that in order to work the problems properly. Lenses are very similar, so that's a concave mirror. It's useful to think of convex lenses in the same breath, if you will. So this is a convex lens. Convex lens looks like this. You can have, this is my object, this is my image. This is a real image. This is my object. This is my image. That's a virtual image. You see how they're similar? Right, the ones on the top form real inverted images. The ones on the bottom form upright virtual images that are bigger. This is like a magnifying glass. This is like a magnifying mirror, like a shaving mirror. All right, and then we also had convex mirrors. The names are switched, so that's convex and concave refer to the geometry, not what goes to the right. And concave lenses. Convex mirror, this is my object, this is my image, that's like a security mirror. A concave lens looks like this is my object, this is my image. In both cases, these are virtual images. Okay? You'll have a convex mirror can only be virtual. A convex lens can be virtual or real, depending on where the object is. You're not going to have any ray diagrams That's right. The concave lens and convex mirror can only have virtual images, only virtual smaller images. It's the concave and mirror convex lens that can have different images. You can think about these as diverging devices. These are diverging. That means that light rays diverge when they approach the mirror, and these as converging devices. I think there was a free response here. Oh yeah, here it is right here. This is a converging. That means that light rays converge on one another when they come together. Okay? You're not going to have any ray diagrams on the test, even though we did have a ray diagram on exam 4. But it would be helpful to look back at the ray diagrams just to get a feel for what types of images are formed. Like I said, you're not going to have trace rays, but it'll be helpful to know how the rays are traced. Can I clear this, y'all? It's important. It'll come up in the multiple choice, like you'll have questions like this. In fact, all of these things, all of these questions you could answer just by knowing those little diagrams, 7 through 10. But it's also important in some of the free response. Let's skip these for just a second. We'll go to the optics. And some of the free response, because like you have to know what type of mirror it is. And so if I have a person that has an upright, smaller image, then I know that has to be a convex mirror. And if it's a convex mirror, remember that has a negative focal length. Diverging devices have negative focal lengths. Converging devices have positive focal lengths. All right, and then you'd have to use your equations. M is negative Q over P, and 1 over F equals 1 over Q plus 1 over P. You will have to use both of those. I think there's one optics free response and several, multiple choice. These were the only two that we had. It could be either one of these. Actually, you know what? It's like number 14. But it could be a lens or a mirror, and it could be, there are a variety of ways it could change this up. Okay? But they all work out largely the same. You just have to be careful with your focal length, getting your focal length the right sign, and then also getting your Q to be the right sign. So I know also that since it's an upright image, it's also a virtual image, because if it's upright, that means the magnification is positive. That also means Q has to be negative in order to give me a positive magnification. So that tells me it's a virtual image, which tells me that Q is negative. All right. So there's lots of information you have to bring together on these. Okay, on optics. Right, we have about 10 minutes. Let's look at rotation. Let's see, how to do cross product here. I think y'all are probably okay with that. Centripetal, huh? The Ferris wheel, yeah, that got a lot of people. All right. We did a problem like this in class, but there wasn't one exactly like this in your homework. There was one that was a little bit similar. Ferris wheel, you have the bottom and at the top. At the bottom, you have the normal force and you have the weight. And the sum of these forces is equal to the mass times the acceleration, and our acceleration is our centripetal acceleration. The direction of our centripetal acceleration is in that direction. Up here, you have the normal force and the weight. And the direction of our centripetal acceleration is in that direction. So it's because our centripetal acceleration changes direction between the top and the bottom, they gave you different answers for the normal force. I mean, you should get a lighter normal force at the top. If your Ferris wheel went really fast, right? Because it would be at the top where you'd fly up out of your seat. Because that's where your normal force would be the least. So I would say sum of the forces in the y direction equals MAC. That's Fn minus Fw equals M And I'm going to put a negative AC here because it's in the negative direction. And then solve for Fn. That's for this top scenario. Over here, I have Fn minus Fw equals m times positive AC because it's going in the positive direction. And so Fn equals Fw plus MAC. Then you had to figure out what is the centripetal acceleration. The centripetal acceleration, I was given omega is equal to v squared over r. That's on your equation sheet, but it's also omega squared r. Omega is not in the SI units, so you have to convert it to SI units. So omega was 0.1 revolutions per second. In radians per second, a revolution is 2 pi radians, so that's 0.1 times 2 pi, 6.63 radians per second. Thank you. And then you can solve for AC. This is whatever it is. And then you put it in here, and you solve for the normal force. It's a little bit different than what we had in the homework, but it's really just applying Newton's second law. Sum of the forces is mass times acceleration. All right? Am I clear? Sure. Yes, quite a few folks missed that. Getting the I cross J, I cross K business. I always like to draw my coordinates. This is I, J, K. I cross J equals, I let my fingers go in the direction of I, like this, with my right hand. They fold towards J, right? I could do it like this, but they have to go like this to fold towards J. And then that tells me that K is out of the page. So that's positive, yeah. The positive K is out of the page. So I cross J is K. I also know, because of the way cross products work, that J cross I is equal to negative K. And you could do the right-hand rule again to verify that. J, and then I have to rotate my hand this way to fold towards I, and that's negative K. There are really only three that you need to know. I mean, you could memorize them if you want. I don't like to memorize stuff. J cross K is I. Right, let my fingers go in the direction of J. They fold towards K, and my thumb goes in the direction of I. J, fold it out like this, so your fingers come towards you. Your thumb goes the I direction. This isn't terribly important right now. In fact, if you're in Calc 3, when you get into Calc 3, you'll learn a slightly different way to do cross products using a matrix. But next semester, when we get into magnetic fields and stuff, it'll become more important then. All right, and then the third is K cross I. This is trickier. K, fold towards I, it goes up. So K cross I is J. I don't think I counted off a whole lot if you missed that. But some of you just sort of added the numbers together without even any regard for the vectors. And you can't add I, J, and K components together on separate axes. All right? Is that clear? All right, and I think the last thing was Newton's law problem like this. Finding the net torque, nothing fancy, something similar but maybe different shape, different force maybe. But you first had to find the net torque. Here I had two forces applying torques. You need to ask yourself, are these positive or negative torques? F2 causes it to move, what, counterclockwise, so this is a positive torque. This is a negative torque because it makes it move in the clockwise direction. And then the net torque is just adding up those. So, Fr sine theta, F is 20, R is 2, sine of theta 90 for this one, so that's 1. And then you do the same for F1 using sine of 30. And then once you find the net torque, it is whatever it is. Uh, you have to find the moment of inertia. I have to look on your equation sheet. This is a cylinder or a disk, so it's 1/2 mr squared for a disk or cylinder. Uh, find that moment of inertia, and then you have to find your angular acceleration, which is torque over I. Once you find alpha, it becomes a kinematics problem. You have to find omega for part C, which is omega naught plus alpha t. But you know t, and now you also know alpha, so you can find that. And then once you find that, you can find the kinetic energy, which is 1/2 I omega squared. Something similar to that. You have a rotational Newton's second law problem. Any other questions, Joe? That's the test. There's a lot on it, right? It is a long test, but there's a lot of material. And, a lot of it's just going to go really quickly for you, and you're just going to zoom right through it and have no doubt about it at all. And other parts where you might have to stop for a little bit and work more carefully on it. Okay? We will meet at 7:45, and I'll send you all an email this when I get back to my office. 7:45, and we'll keep y'all till 10:15. Okay? Alrighty. I will see you in the morning, 7:45.